Good afternoon, everyone. So I'm glad to continue this session with you. A quick recap of what we spoke about yesterday, a refresher. So basically, we saw what does artificial intelligence correspond to. We had this symbolic type of artificial intelligence that corresponded to expert systems. We also had these sub-symbolic artificial intelligence systems such as machine learning. We saw that regarding machine learning, we had two main types of problems: supervised problems and unsupervised problems. Supervised problems corresponded basically to problems where we had a target to predict, and we had some explanatory features that we could use, and the training of a model was simply done by splitting historical data into 70% of observations that were used to correlate the target with the explanatory features, and 30% was kept aside so that we could use these observations and ask the model, what would you predict for these observations? Compare the predictions for the target variable with the actual values of the target value variable on this historical data set. And then we could compute the performance of the model. And the other type was basically unsupervised machine learning, which basically corresponds to features of observations. There is no target to predict. And the goal was to group observations in similarity clusters, for which we still had to produce a domain interpretation or explanation. Then we saw that in the field of AI ethics, we could focus on three building blocks to analyze this problem: basically intelligibility or explainability, non-discrimination, and auditability of models. We also saw that well, we could draw a parallel between how the administrative order of bureaucracy had very strong historical ties with the advent of computation and computer science, and how the fact that we could produce large-scale bureaucratic systems, either state in the public state or in corporations, precisely because of certain properties of classical computer science procedures, such as easily explainable programs and an explicit representation of knowledge in these programs, for example, as a set of rules. We also had this very important property of explainability by excerpts. Basically, we could, in a decision program, quite easily spot the relevant part of the explanation to produce. And then this was not necessarily the case with all machine learning algorithms. Of course, we saw that for a decision tree, we had very explicit data space segmentations because we know what are the dimensions and we can formalize in the form of inequalities the data space segmentation. We saw that if we evolve into more complex models, such as regression models, we could still formalize the data space segmentations, but the dimensions of the space could have more complex forms using square roots or powers of the variables. And finally, we saw that in the complex case of deep learning, we can sometimes have none of this. Basically, we can have space dimensions that are not interpretable at all, and also have data space segmentations that cannot be easily formalized in the form of equations or inequalities. And this is specifically the case for all the intermediate layers of a deep learning network. So with this in mind, basically, we started dwelling into each of the three components, basically explainability, and then discrimination and auditability. So we just had the time yesterday to start speaking about what do we mean by explainability in the context of machine learning. We saw that a very important notion is the distinction between explainability of the procedure as a whole, basically the split of the data, the creation of features, the training of a model, how the algorithm that is being used is can be explained and analyzed, etc. And explainability of the output of an artificial intelligence model, basically the explainability of the produced decision. And this distinction is very important because often, and this is somehow a sociological conjecture, people, when asking for explainability, ask only for an explainability of outputs. They do not really care about a pedagogical explanation of how the deep learning algorithm producing the decision works. All they care about is the explanation of the output and see if this makes sense to them. And in order to be able to be more precise and formal about this notion of explanation, we stopped at this section, which is how can we achieve a formal approach to this notion of explanation so that we can have something that is a bit abstracted from the inner workings of the models. So as we saw, we can make two types of conjectures. A first type of conjecture, which is the sociological conjecture I was evoking. So basically that most requests for explanations are requests for a local explanation, an explanation of the output or decision of the model, and an epistemic conjecture, which is the fact that we can satisfy this type of request without focusing on the details of the procedure or the model. And if we translate these two conjectures into a formal approach to AI models, this basically means that we consider the artificial intelligence model as a black box, since we do not care about the details of the procedure. And then we have input data, and we have an output which would correspond to a decision. And we saw that by focusing on this very simple framework, we have some very interesting characteristics for the explanations we are able to produce. Mainly the fact that we are able to identify the factors in a given decision because we have access to all the input data. We can, for example, see what is the order of significance of these parameters in a given decision. We can also check out if we are using or not protected variables such as race or political opinion or other proxies to these protected variables. We saw that we had a second very important feature for explanations, which is the ability to check consistency between decisions. So we can, for example, take two very similar inputs or an exact similar input and produce two decisions in a row and see if we have robustness, stability of decisions, if we have inconsistency, if, for example, two very close examples have very divergent decisions. And we can also check for threshold effects, basically decisions that change a little bit too much if a variable slightly changes. This can be normal, it depends on the use case at hand, but it can also be an undesired effect and which has to be checked, and you can check it through this very simple framework for the notion of explanation. And finally, a third property for explanations in this framework of black box reasoning, which correspond to counterfactual reasoning, meaning the ability to well, imagine and compute what would happen, what would the decision be for different scenarios of input data. And this is important because it allows users to adapt their behavior and strategies if they are facing algorithms and interacting with them, because then they could imagine different scenarios, change the input data, and see how the decisions would have changed. And based on this information, they have a weak sense of causality that can guide them in their behavior and in their strategy adaptation. So basically, if we take this framework, we also saw that if we compare it to this notion, if we try to see what would link be with the notion of explainability by excerpts, we saw that the connection is not that easy to make, in the sense that this black box approach does not include any simplicity criterion on the input data. Here, basically, your input information can be very complex. You can have millions of input points, and you can also have very abstract input data that is not always necessarily easily understandable. So you cannot guarantee a simplicity of the explanation in this framework. Whereas the explainability by excerpt basically means that you are able to produce an explanation with very few criteria and intelligible ones. So this would be still a problem, for example, to solve even, and we would have to extend the framework into something a little bit more elaborate. The two main types of limitations that you can find in the literature regarding this framework of black box explainability. The first type of objection is that we need to supplement the model with conditions on input parameters intelligibility, so that we can at least impose or be sure that we do not completely hide all interesting information in millions and millions of input parameters. But this is not a condition of the initial model, so it's a new and supplementary condition that needs to be added. And the second type of objection is that this limits the explanation to pure correlations. This is not necessarily a problem in the case of machine learning, because basically machine learning works based on correlations. You have no direct causal connections that are captured and modeled by the machine learning model. All it does is capture correlations between, for example, the target variable and features. But since we are speaking about an abstract framework for explanation where the inner workings of the procedure are just a black box, this shows that, for example, if by opening the black box you see that you had a deterministic model that takes into account causal relations, well, since you suppose that you do not have access to this information, you lose this ability to analyze the causal relations, and you can only focus on the correlations between inputs and outputs. So this objection is problematic for the framework in the case we are analyzing all types of models, including causal ones. But it's not that problematic in the case of machine learning, since even by opening the black box, all we would see is a machine learning model, which is itself based on pure correlations. So regarding this first objection of intelligibility of input parameters, it's an important one in the sense that, like the arguments we made yesterday, you use machine learning precisely in a context of complex data spaces, high dimensional data spaces, where some non-intuitive factors might intervene in the final outputs and decisions. So it can sometimes be hard, even for the scientists or the engineers producing the model, to produce a good understanding of these input parameters. And then it would be very hard to apply causal reasoning, or at least weak causal reasoning, to this if you have no understanding of these parameters. And regarding the second type of objection, here the thing is that you can of course say that well, since machine learning is based on correlations, it's not that of a big issue not to be able to produce causal explanations. Intellectually we would agree, but practically, for example, we do consulting for multiple firms on and build for them artificial intelligence systems, etc. And what you see is that very quickly, once you did the proof of concept and people get familiarized with what is machine learning, how does it work, how does training work, etc., very often when they have to make decisions, giving them explanations based on correlations is often insufficient, because they want a causal intuition behind why, if I move A, then B will happen with a certain probability. What is the causal connection between the fact that acting on A will influence B? Oftentimes we have some kind of intuition, some kind of business intuition between the features and their impact on the output, etc. So this is good because we are base ourselves on this business or domain intuition to provide weak causal explanations. But in some situations where you're exploring completely new data spaces, etc., and there is no such intuition, well, making decisions based on purely on correlations with no previous understanding of what is the relation, what is the deterministic or quasi-causal relation between variables, can be really a hard sell. So the issues raised by this absence of a strong causal understanding cannot be solved by this weak or perturbative view of causality. And beyond this problem of causal analysis, it can be very hard to prove, for example, intent in the situation of black box procedures. We had the example in recent years of Google artificial intelligence classifying images of African persons as gorillas. So if we use this framework of a black box where we only analyze correlations, etc., it would be very hard to produce explanations that show that there was no intent to produce this prediction of gorillas for African persons. So so it shows that this framework is probably not enough for an advanced auditing framework. It is good for producing explanations and quick analysis of decisions, consistency, counterfactual reasoning, etc. But if we need advanced explanations for the auditing, etc., it can be a hard sell to use only correlations and base our explanations on this black box framework. So these are two objections, but nonetheless, the framework is very useful in the sense that, as I said, it allows for a right to appeal from a given decision or challenge the procedure for consistency. It allows users or citizens to adapt their strategies to defend their interests and rights. So you have this incentive channel that we spoke about, the incentive channel of government that is maintained. And of course, as I said, you can control the use of protected variables and what is the impact of the decisions on certain subgroups, for example, through threshold effects. And this allows a control of fairness. And now we will start the second part, which is about non-discrimination. We see here that this framework of explanation can help us account for discriminatory situations, which is a very important feature of this framework of explainability. So now we can ask ourselves, okay, if we are to deal with this notion of non-discrimination, how do we define fairness? How do we define non-discrimination? And once we have this definition, we need to ask ourselves, what are the root causes of unfairness in artificial intelligence models? And what are the concrete solutions that we can build to, well, make the artificial intelligence assets more fair? So here, to give you some examples and intuition about what we are speaking, there was a small scandal about how Amazon advertised their recruitment. Basically, most of their recruitment ads were displayed for male candidates. And when they had this point was challenged and they had to analyze the used algorithm, they said that they did not use the sex variable. So they were quite surprised by this result. But by analyzing further, what they saw is that since there is a trend in reality for having more men being recruited in engineering at Amazon Web Services, which is the cloud company of Amazon, since there are more male former employees there, basically when they analyzed the resumes, they had more male resumes than female resumes. Even if they erased sex, you still have more resumes that were male resumes versus female resumes. If there were only, for example, schools or skills, etc., in these resumes, then there would be no difference, noticeable difference. But the thing is that there are hobbies often in these resumes, and hobbies often depend on the gender. So basically, what the model had as data was a set of resumes where there was this huge disequilibrium between male type hobbies and female type hobbies. So what the model learned is that basically most of the candidates and the good candidates have hobbies that correspond to male hobbies. So even if they did not use this sex variable, through this proxy variable of hobbies, the algorithm learned that, well, probably good candidates are of this type, and this was reflected in the fact that they tended to recruit more male than females. The second type of problem that we can have is discrimination, for example, on skin color. And here you can look out for the Compass software, which is a very good case study for non-discrimination. Basically, if you look at two individuals, one with the white color and the other one with black color, what you see, for example, in the first comparison is that we have a black person with very high risk scored as 10, and a white person with very low risk scored as 3. Just a quick second, I will close this Slack. And when you analyze the details of the risk for these two persons, or for example, for the woman with grade 8 and the male with grade 3, or the other of two persons, basically you see that the prior offenses of the black person are often smaller than the prior offenses of the white person. And you can also have situations where there were no subsequent offenses of the black person, and the white person had subsequent offenses. This software is used basically to decide on parole liberation in US courts. And what you see here is that, well, scoring for two individuals is somehow inconsistent. You have black people with the objectively smaller risk than white people, but which end up with a higher risk notation. So this can be considered as very problematic, since the intuitive definition of non-discrimination would be that, well, if I have two individuals, I should have exactly the same decision by not using for example, the protected variable. But we will see that the problem of non-discrimination is really more complicated than that. So basically, you can have two types of discriminations that we need to define. There is the first type of discrimination that is called disparate treatment. So here, basically, you are using the protected variable to make decisions. For example, you can decide to hire or not certain persons, and you use sex as a variable. So here you are doing a disparate treatment based on the sex variable. But you can also have discrimination without using the protected variable. And in this case, you are in a situation that is referred to as disparate impact. Basically, you do not use the protected variable, but despite this through proxy variables that are correlated to this variable, for example, revenue or a geographic localization as a proxy, for example, to skin color, etc., you can have a disparate impact on groups characterized by the protected variables. For example, you can be harder on jailing on black people, or you can harder on controls in the streets, etc., despite not using variables such as skin color, but you are using, for example, average revenue, etc. So we can see here that protecting variables is not the solution to non-discrimination. The problem is much more complicated than that. And even more than that, you have different definitions, possible definitions of fairness. So a first type of definition is a definition referred to as anti-classification. So basically here we have some protected attributes like race, gender, or their proxies, which are not used to form predictions. So basically we protect some variables. And this was the case for the Compass situation or the Amazon situation. They did not use sex variable, and they did not use the skin color to train their model. But for this definition of non-discrimination, you ask that two individuals with same attributes or similar attributes will have the same score. But if you ask for this, and it can be a very good definition of non-discrimination, we can show mathematically that you can have a distribution of decisions that can be different for each class. If I average all decisions, for example, for the black people, and average all the decisions for the white people, I can see, for example, that, well, if I impose that I have exactly the same decision for two individuals with same characteristics, if I average, I can have a higher jailing rate, for example, for black people for the same risk versus a lower jailing rate for the white people for the same risk. And this is due to the incompatibility of this definition of anti-classification as non-discrimination with the second type, which is classification parity. Classification parity asks for equality across classes defined by the protected attributes. So if I want to impose this classification parity, meaning that I have the same decisions across classes, then I would lose anti-classification, which means exactly the same decisions for people with the same attribute. And if we go back to this Compass situation, we can see that the company that made the software basically chose the second definition of non-discrimination. They chose the classification parity. So they decided that we would have, on average, the same risk notation for black people and for white people. But this can lead to discrepancies at the individual level. We can find situations where two individuals have exactly the same characteristics, but a different grade, simply because we wanted to have, on average, the same grade for risk. And there is also a third type of definition. You can there's of course more than 3 types, but I mentioned here the 3 main types of possibilities, so that you can at least have them in mind. The calibration, the definition of non-discrimination. Here, what you ask for is a bit more complex. You want the decisions to be independent of the protected attributes, conditional on predicted score. So we want, for example, to decide on parole liberation or not, independently of skin color. And we want that what happens after liberation exactly corresponds to the score. So if my score is of 8 out of 10, I want to verify in real life that after liberation, there is a risk of 8 out of 10 of, for example, new offense. And this can be very hard to achieve, in the sense that you cannot always observe what happens if you end up jailing people. You cannot observe what would have happened if they were not jailed. So it's a bit more complex criterion, but it can be used if you want to have a stronger mapping between the notion of risk score and probability of an event happening in real life, which is not necessarily guaranteed with the 2 former criteria. Do you have any questions on the first part about explanation or non-discrimination? Okay, so if there are no questions, I will continue the presentation. So we can ask ourselves, what are the root causes of discrimination in AI system? I think someone asked yesterday a question about, well, we can have a discrimination due to the training of the model, but you can also have discrimination already present in reality. And this is exactly the case. Data generally is just a not so objective translation of reality, and the reality itself can be biased due to historical reasons, sociological reasons, etc. So we have a very long chain of root causes of unfairness in building models. But if we analyze, for example, as we saw yesterday in analogy with bureaucracy, we see that standardization of procedure, even if it makes it more objective and bias-free, it is bias-free from the point of view of the operator or the executant of the procedure. But it is false in the sense that we still have the designer bias. The person that is designing the system can still have the bias, and it will he or she will introduce this bias into the procedure. So if we focus on what happens, if we put aside biases already present in a reality, if we focus on building the procedure, then you have a bias in the training and test data selection. You can have bias in the way you made your feature engineering. For example, you can add a variable which might be a protective variable or not, or transform this variable in such a way. For example, if you have age and instead of using a numeric variable age, you, for example, define bins or inequalities, young people versus old people, etc. And the threshold you are choosing can really influence the way your model will behave. We have a bias in the performance metric that is being chosen. You can also have a bias in the way you are selecting your model and tuning all the parameters of the model, plus all, of course, the psychological biases that influence each of these steps, because after all, it's humans and engineers that are building these models. So an important example that you can think of is that it has been proven through various studies that when they analyzed the decisions that were made by judges in courts, and they saw that basically for very, very similar cases, the decision at the beginning of the day at 8 in the morning or 9 in the morning, for example, was different from the decision right after lunch. And that the psychological mindset of the judge was very important and introduced bias in the way that justice was rendered in these courts. So this is an example that you can imagine is probably exists also for the case of engineers or all other parties that intervene in the development of AI systems. And of course, we have this proxy problem, basically the correlations that exist between variables, which might lead an artificial intelligence model to, have a certain bias or have a certain discrimination regarding a feature that is not used, a protected variable that is not used for training the model. So this is basically a problem that is very hard to get rid of. You still have, if you want to analyze it, you would have to analyze the correlations between a protected variable and all other variables. You need to be very careful in the way you do your feature engineering, etc. So what are the concrete solutions then if we want to build AI systems that are more fair? A first step, for example, could be to imagine and formalize the so-called discrimination impact assessment. Here, the analogy is with the privacy impact assessment, which already has a framework developed after the regulation in Europe on personal data. So privacy impact assessment is a document with a checklist where you have to answer specific questions on all the measures that you are taking to mitigate all risks on personal data. And we can imagine something that could be very similar to assess the measures that you made, or and all the steps you imagined and procedures to mitigate the risks of discrimination. A second possible measure is the use of frugal models. By this, I mean that we should minimize as much as possible the features we are using and be able to understand them very well and explain them. And this might seem obvious, but this is not a common tendency in the data science community. For example, back in the years when I personally was developing models in 2014 to 2015, basically all data scientists around me had an approach to model development where you just had to pick up as much data as possible on your problem, and then build as much features as possible. Generally, you can turn, for example, 2 or 3 features into 30 features if you have a certain notion of dynamic evolution. So you look at the feature at -3 months, -6 months, you build ratios on the value of the feature, etc. And you can very easily end up with a model with 200 features. Detecting what are the threshold effects, what might be the biases, what might be the discriminations if you have 200 features is very, very hard. So this is generally not a good approach if you want to minimize risk on non-discrimination. You should aim for using maybe 10, 15, 20 at the most variables, so that you have a very good understanding of these variables and their effect on the groups or populations you are treating and you are creating decisions for. And this is also interesting not only from the point of view of ethics, but simply also from the point of view of good engineering and good industrialization anticipation. Because again, often in the proof of concept phase, you can decide to use hundreds of variables and build them, etc. But if you want to industrialize your model, then you would need to automate data flows. And if you used a lot of different sources, a lot of different variables, well, the probability that the data quality of certain sources is not always very good, or the probability of an error in the loading of data and transfer of data, etc., gets higher and higher. And so the probability of a bug in your industrialization gets also higher. So it is really a good practice from both the point of view of industrialization and from the point of view of ethics to minimize the number of variables that are being used to build your artificial intelligence systems. The third possibility of solution to build fair AI systems is model penalization during training. For those of you who are maybe familiar with model penalization, basically you can think of the linear regression. How do we find the straight line that goes as close as possible to all the data points? Well, basically what you do is to compute the distance between the points and the line, and you sum the squares of these distances so that you have a certain metric that you want to minimize. By minimizing this sum of the square of the distances, well, it means basically that probably the line is the closest possible line that goes through all the points. So this is the metric that we use and we want to minimize during the training, and we can penalize it, for example, for various criteria. For example, if you are using a regression model, you can add to this metric the sum of the square of distances. You can add the absolute value of the coefficients of the model. And if you want to minimize this new function, well, basically you can minimize it by having coefficients that are as small as possible. And this is interpreted as a constraint on the complexity of the model. Basically, you're asking this new metric to optimize both the line, but also the fact that the model should not be very complex in terms of coefficients. So this is done to avoid, for example, overfitting of your model, but we can imagine adding other criteria to this and changing the function that needs to be minimized so as to avoid a certain bias, for example. And I do not want to get into a lot of technical details, but you can add certain coefficients that will avoid bias on certain protected variables or certain groups or certain types of target variables, etc. So this is probably the most technical way and the last way you would like to explore after discrimination impact and minimizing the features used. Then you can decide to dwell into how can I modify my metric to be minimized in order to penalize any type of bias. It's a complex step. It's not really straightforward, but if you understand your problem very well, if you chose your target in a certain way, if you explored what are the possible biases in your data, then you can come up with interesting ideas of what to do on the function to be minimized in order to penalize possible biases. And finally, the fourth type of solution that you can imagine to build fair AI systems is the so-called adversarial modeling. Basically, the idea here is to say that, well, often we model our systems, etc., with a too optimistic mindset, basically that everything is working fine and will work fine in any environment, etc. And whereas adversarial modeling is a tendency to imagine worst case scenarios and test them concretely at each step of your development. So basically you could imagine that, well, I probably have a very strong threshold effects on populations, and test your model against this and imagine new observations that, for example, that might be in limit situations and see how the model behaves. And by this, you build an understanding of the limit behavior of your model and see what are the weaknesses that you might correct and what are the possible and potential sources of non-discrimination. So this is really the last step to be performed after you've done the first three. It's not a science, it's not something very precise, but you can always take inspiration from the practices of other companies, etc. For example, Netflix is very known for an adversarial approach to building their systems, being AI systems or purely technological and technical systems, etc. They have, I think, even a practice called chaos monkey or something like that regarding the way they develop their system. They always aim for problems, and they sometimes create problems themselves to ensure that the robustness of their systems. So this was what I had to say about non-discrimination. If you have any questions on this, please do not hesitate to interrupt. And finally, regarding the auditability of artificial intelligence systems, this is quite complex topic in the sense that, we can generally think of other domains or jobs, etc., where auditability is much more well defined. For example, accountability has norms, that has frameworks that are studied in university, has some standards that are internationally agreed upon, etc. So this makes the auditing of, for example, financial functions of a company or some technical functions of a company, etc., quite straightforward. But when it comes to artificial intelligence, machine learning, or data analysis, etc., it's very hard. We have no real standards. We have no specific training or university programs dedicated to this type of problems and jobs. So we have to go from the basic principles of how these models work and see what frameworks we can develop in order to ensure a better auditability for the systems. So here, if we split the data and model lifecycle to try to imagine a good auditability framework, we see that we can start with the input data, which is the green arrow at the top of the figure, and then we can start a phase of data preparation. So basically, when you have your data, you start by cleaning it. By cleaning it, we mean, for example, that you either for example, delete or transform or change, for example, if the dates format, if you have inhomogeneous date formats, etc. You can also treat missing values. You can also treat obviously aberrant errors, for example, an age of 300 years, etc. So you clean your data and you correct all the problems that you might face. Then you go to the step of labeling your data. Either you have obvious labels, for example, people did or did not subscribe to a contract. So you build your label 0 or 1 depending on what you observe. Do they have a contract or not? Is it still active or not, etc. Then you perform your data analysis and transformation to arrive at the matrix that I gave as an example yesterday, which is basically this step of the development. You already had some raw data that you had to clean, label, and transform before arriving at this table or matrix structure with observations, features, and the target variable. You validate your data either with business experts or through some statistical analysis. You do some feature engineering. Basically, you build new characteristics for observations, such as ratios, for example, between, I don't know, maybe revenue in year 1 and revenue in year 2, etc., to see evolutions of certain features. And you split your data between trained data, which would correspond to 70%, and the test data, which would correspond to 30%. So this is the first building block, basically data preparation. And then you go to the second building block, which is the model creation. So to build a model, you optimize the way you are training your model. So you set certain parameters, for example, known as hyperparameters for the model. You train your model, then you validate your model on this data, and then you can retrain it at scale, meaning that you retrain it on the whole of your historical data to use it in the production environment. So now you have your model, and we have the third step, which would correspond to the inference, basically using the model to produce new predictions. So what you have to do is take your model, which now corresponds to a file, for example, or an API, etc., and you deploy it either on a cloud platform or on-prem service. And now we have new data incoming, which corresponds to this second green arrow of data incoming. You have your model, which can be served with this new data, and the model will produce predictions, and you need to monitor these predictions and infer what is the state of your model depending on these predictions. So you have to monitor these results. Do I have coherent and consistent results? Is there a deviation, for example, from the average value of the results from the historical average value, either for features of the or for the predictions? You can do some logging of these results so that you can have some traceability of your model, etc. And you can add an explainability layer, either to end users or business experts or data scientists, etc. And depending on the results of this monitoring and logging, you can do some fine tuning and improvements of your model. And this allows you to go back either to the data preparation phase, or more often just to the building model phase. Basically, you need to retrain your model, etc. So in a very macro view, this is the data and model life cycle. You have some transverse thematics, which would correspond, for example, to the exploration and working environment. So this is the technical setup that you are using to do all these steps. You can also have the transverse problem of data flow and workflow orchestration. For example, when do I launch the job of data extraction? How do I automate it? How do I automate the retraining of the model, etc.? And this can be done through various tools, etc. And finally, you have the versioning of data and the checks of consistency, which is a transverse problem to multiple use cases. You do not check for data consistency model per model. You do this at an abstract level for the data per se, and then you use this consistency to then serve this verified data to various models. So it's a transverse problem. It's not specific to a certain model. Do you have any questions on this life cycle?
Sir,
Yeah.
sir, in the first step of data preparation, can you just explain what does the feature engineering mean, sir, after data validation?
Yeah, of course. So imagine, for example, you have as features, we go back to the example of contract subscription we saw yesterday. So we have your target variable of 0, 1, etc. for the individuals. And you have, for example, sex, revenue in year 2018, revenue in year 2019, and revenue in year 2020. So you can use this raw data as features, but you can also build new features, which is called feature engineering. For example, what is the evolution of revenue between 2018 and 2019? To do so, you would take the ratio between the two revenues at the two different years, and this would produce a new information, for example, 30%, that you will add as a new feature to your matrix. And for each individual, you will have a ratio of evolution of salary between the year 2019 and 2018. And you can imagine a lot of new features like this. Does this answer your question?
Yes, sir. Yes.
Okay, perfect. So now that you have this life cycle in mind, we saw that, well, you can have a lot of things to consider. So what should we focus on now that we understand what is the life cycle of developing an artificial system model? So if we want to really focus on the most important aspects, I summarized here the 8 most important ones. Basically, you can start by looking at your model and the way you did your modeling. Is the model and all the pre-treatments you did argued, reproducible, and ethical? In the sense that if you do all the steps here, but by serving in the last row, by serving 2 times the exact same data, you see that you have very different results. If you did not do this check step and well documented and justify that indeed you have a reproducible model, you are not auditing correctly your system. So there is a very important step that is purely focused on the model, its reproducibility, and the type of treatments you are performing. Then you can check for the robustness. Do I have stability over time accompanied with uncertainty estimates? This is a very important point because most of machine learning algorithms do not give uncertainty estimates. They just give a prediction. The prediction is, for example, for this individual, the score for subscribing is 0.7. And even by imagining this score 0.7 can be interpreted as a probability, which is not always guaranteed. It just says that there is a probability for the person of 70% to subscribe the contract. But what is your error margin? Most models do not give this information. So if you want to have a good ability to make decisions, you need, of course, a certain probability, but you need a confidence interval around this probability to be able to produce decisions. Because if the probability is 70% plus or minus 30%, then it means that your true values for what would happen range between 30% and 100%, which is too large to make good decisions. And this is often overlooked. We start today to see that companies, business experts, domain experts understand that a score prediction by itself is not sufficient, but for many years, they did not ask for this information. They were just happy with the score, imagining that it was sufficient for itself. So robustness and the ability to say what is the certainty of your decision is very important in auditing AI systems. The third step is the intelligibility. Did you build all the blocks, interesting blocks, to be able to explain the predictions to a non-expert? So here we are focusing, as presented, on explainability of outputs. For auditability, we do not necessarily care about production of the explicit explanation of the whole procedure, because if you do all the steps, the procedure will be by itself self-explanatory. But one of the important steps to guarantee this auditability is intelligibility of the outputs. The fourth step is to focus on the code. Is the code modular? And by modular, we mean that you did not write a unique script with thousands of lines and the hundreds of functions that needs to be executed to launch your model. By modularity, we mean that you build one script per function, and each function is a very simple function that does a very defined and predictable operation on its inputs to produce outputs. And by doing this functional way of coding and modules, then you can very quickly understand what does what in the set of scripts you have, and see what are the relations between functions. And of course, your script will probably be much more light, because you can use one function in several functions as a sub-function, whereas if you just write one script, you might have to reproduce the code of the function in several zones, hence making your code much longer. Did you version your code? For example, you might have a first version for all your modules, but then with time you needed to add new features, new functionalities, etc. We often see that people just change the code of their functions. But since you already made decisions based on the older versions, how can we check how did you produce these decisions if we do not keep the old versions? So versioning of code is a very important notion. And finally, did you perform the so-called unit tests? Unit tests basically correspond to the tests on these modules that you developed, and predefined tests. For example, if I have this and this and this input, then I expect to have this output. And you define these tests and perform them each time you do modifications on your code to check basically that your function is still working as expected. And this is, again, not so common practice in the data science community. Of course, it is already a widespread practice in software engineering, classical software engineering, but in data science, we often see too many data scientists developing models and not performing unit tests on the functions they develop, or having highly unmodular code, etc. So this is the fourth important step to guarantee auditability of your systems. Build modular code, version this code, and define tests for each module, and perform tests at each moment that you modify the modules of your code. The fifth step for auditing is to have very good and predefined monitoring indicators and steps. For example, you can define an indicator that measures the performance of your model each 5 minutes. For example, if it's for example, an advertising model that needs to be refreshed very quickly, or once a month, for example, if it's a model of fraud detection. Fraud does not change in nature each month, so you can have a lighter rhythm of verification. So this is related to the performance of the model, but you can also verify the stability of your data. Did I have a drift in the data regarding, for example, the average value of age in my population? Because if I see a drift in the average age, then probably I should change my model, because if population has changed, probably the historical data I learned from to perform decisions is not good enough anymore. And finally, the third type of indicator that you need to monitor is the return on investment. You can have very good performance on historical data. You can even have very good technical performance. For example, your model does very good predictions on new individuals that you are collecting data for. But for one reason or another, you see that you cannot transfer this technical good performance into business performance. Simply, for example, because you are predicting that this person will subscribe the contract, and this other person will subscribe the contract, will not subscribe the contract, etc. But if on average you see that the people that decide to subscribe the contract subscribe it only for a month or two, and then cancel or churn and go to a competition simply because you had, for example, some commercial offering, etc., interesting for a certain period of time, you will see that your investment in good prediction model does not translate into good business performance, because, well, you did predict that people will subscribe and push to them this interesting offer, but then this is a volatile population that you do not really want as a client, since they will not be with you for a very long time. So one should really distinguish ROI, business return on investment, and technical performances. So these are three types of metrics that you can monitor, but of course you can imagine other types of metrics in order to continually audit your system. The sixth type of important information to audit is alerts. How did you define your alerts? Basically, alerts are strongly tied to the monitoring phase, because monitoring consists in defining the KPIs that you will monitor, but alerting consists in defining the thresholds on values of these KPIs so that you raise alerts. And of course, the thresholds will be strongly dependent on the business case at hand and the specific application you are considering. And often it is a very challenging step because, well, if you define alerts, the idea is that if an alert is raised, you need to take action. But if you have too much false alarms, for example, very quickly the business teams, etc., will consider that your system is not well built and start ignoring the alerts. And again, if your system is tuned in such a way that you do not always raise alerts when you should have, there will be very little confidence in your system, because business teams will always think of a situation where probably things can go wrong, an alert should be raised, but you did not because your model was not tuned well. So it's a very subtle and complex problem to set alerts in a way that creates confidence among business teams to indeed use and rely on the artificial intelligence systems. The seventh step is the so-called A/B testing. So basically, once you developed your model in proof of concept phase and want to put it into production, well, you need to verify that indeed, when using it in the real world, you do see the performance you saw on historical data. There are a lot of different strategies. For example, if you want to use a model that detects fraud, well, what you can do is, for example, still use your legacy system, which is based maybe on business rules, etc., and use at the same time your new system. But for example, apply the decision of the old system, and then observe what happens. The problem with such situations is that, well, for example, if your old system says that this person will fraud, and your new machine learning system says that this person will not fraud, if you apply the decision of the old system, you will not get a credit for this system, and therefore you will not be able to verify if the predicted decision for the predicted outcome by the machine learning model did realize or not, since you did not grant the credit. So this way of doing, basically just producing decisions but not applying them, is good for certain situations, but it's not so good for other situations like credit granting. So another possibility is simply to split your populations in two. You have a very small proportion of population on which you will use the new model, and a majority of population for which you use your old system. And if you observe that on the small population, the results and the decisions that are recommended by the machine learning system do lead to good technical performance and good return on investment performance, then you can slowly switch the populations and the decisions from the old system to the new system. So this basically corresponds to A/B testing, and it is a very important step to add to a good auditing process. And finally, the last step, and probably the most important one, because basically it concerns all the previous steps, is documentation. Did you document and write on each of these steps, basically the choices of the model, the robustness test you performed, the intelligibility criteria you introduced? Did you comment your code and document all of your code? Did you document all the performance or stability tests you performed? Did you document the way the alerts were created? Did you document all the A/B tests you performed and what were the results, etc.? So it is important for, of course, the ability to audit the system, but also to avoid skill evaporation, because often people move in a company, people change, switch companies, etc. And the experts that developed a model might not be still here 2 or 3 years afterwards. And if you have no documentation on the choices that were made from the technical, scientific, or business point of view, then you will be completely unable to audit the system, but also allow the people that are running the company at that moment or operating in the company to use the model in an efficient way, and of course make it evolve if necessary in an efficient way. Do you have any questions on these 8 aspects of AI system auditing? Okay, if there are no questions, I will pursue. So now that we spoke about the main building blocks, so you can ask, okay, so now what? What can we do to define auditing processes and organizations, etc.? And here is an example of a proposition we do to our clients to organize their auditing processes. First, you need to define supervisors. Basically, there needs to be someone in charge of this auditing and supervision of models problem. And what you need to deliver then is an organization chart with clear responsibilities, so that you do not have fuzzy zones of responsibility, so that no one takes actions in these fuzzy zones. The second step you can do is to consolidate a processing flow. For example, when you think of the data and model life cycle I showed, what are the various tests and verifications you perform at each step of this life cycle to ensure that you are doing things right. The third step is regarding outputs, is to ensure the model robustness by defining confidence intervals. This is important because, as I said, it is often an overlooked step, and you cannot guarantee robustness if you have no confidence interval. The fifth step is to define the alerts system and deliver a drift detector. And as a sixth step, define the so-called failure tree. It's basically, if you need to historize and document all the alerts that were raised in the past and all the solutions that people imagine, so that if you have a new error in production, well, you have a process where people will go and look at the failure tree, see if the problem was already met in the past and what was the solution. And if there is no such failure in the past, well, you try to find a new solution and add this new failure and the found solution to the failure tree, so that you capitalize in time on how you on the problems you had to face and the solutions you developed. The seventh step is to build processes, etc., to adapt for drift and return your model. Then, as eighth step, is to test your solution through A/B testing. And finally, document all evolutions with a historical timeline as a deliverable. So this is a simply putting in a timeline the aspects we evoked in the previous slide. And you can think that, well, all this is seems great, etc., but it seems very complicated. How can we do for companies that have, for example, 1,000, 10,000, 100,000 employees? How can we build robust AI systems, etc., with so much different data? How can we ensure robustness? How can we deal with all this? And of course, if you are in a centralized paradigm for data management, it can be very tough because, and this is just, unfortunately still the situation in most companies. So basically, we are in the situation on the left figure where you have a lot of data sources, sometimes tens or hundreds or thousands of data sources, and you have a centralized platform. either a classical platform or a big data platform with a lot of the so-called ETLs. ETL is an abbreviation for extract, transform, and load, which basically corresponds to a pipeline of data treatment where you extract data from the sources, operate certain transformations, and then load this data into different tools or databases. And then you have consumers at the end of this centralized platform. The problem here is that, well, as said, the platform is centralized, but what this means is that it translates into centralized teams. Basically, you will have data engineering teams which are centralized and focused on managing this data platform. And the problem now is that this team has limited resources. So more often than not, they will have too much requests and will not be able to deal with all the requests, hence creating a bottleneck in the treatment of problems of the various teams that are trying to leverage data. And since these teams will not have access to for example, if they notice that there is a problem of data quality, they will ask for a correction. Correction needs to be done on the centralized platform. Data engineers do not have the time, so correction will not be done. And either you have to abandon your project of model, because when you was in a proof of concept, you could manually correct the data. But now that you need industrialized and automated data flow, if the data engineers of the centralized platform do not correct the data at the source, you will always get problematic data, and you will need to operate very heavy transformations that you are not able to do on your specific level. So centralization is really a big problem for performance of models, for transition rate from POC to industrialization, but also for auditing problems, because you will not be able to correct problems you find in steps here around robustness, intelligibility, code, etc., if you have bottlenecks at the engineering level. But there is an alternative paradigm towards more and more decentralized responsibilities, which is referred to as the data mesh paradigm. So here, basically, the idea is to say, well, we should not have a centralized platform and centralized data management and centralized extract, transform, and load pipelines. We should leave this to the business domains. Each domain probably needs some types of data and produces other types of data. So basically, we let them define their ETL pipelines, the data they need to extract, the way they want to perform transformations, and the way they load this information and share it with others. But what needs to be defined at the central level is governance and standards. For example, how do they document the data they are producing? How do they give access to other domains for exploration of their data? And how do they define, for example, their pipelines in terms of architecture, etc.? And by doing this, what you do is decentralize complexity that is specific to business and centralize management of data for transverse aspects regarding governance, standards, and infrastructure. So, for example, you can imagine a technical team that is managing an infrastructure, for example, for users, etc., but that leaves all the aspects that are specific to data itself to the business domains. And this allows each domain to be responsible for the auditing of the whole life cycle that we mentioned previously for data. And if these teams, some teams, business teams, are producing AI systems, well, basically an AI system is simply a data system. It takes inputs and it produces outputs. And we do not care if the intermediate layer of transformation is an AI system which uses the input data to train itself and produce a decision, or if it's simply a set of rules or basic transformations on the input data to produce output data. So it's very interesting framework in the sense that data transformations are very abstract. They can be artificial intelligence, they can be simple business rules, etc. But what matters is defining standards on how you document the data you are producing, either business data or predictions of AI, etc. And what are the standards to share this data from one business domain to the other. And this avoids the bottleneck of data engineering teams, which are only in charge of developing the infrastructure on which everyone will rely to load, transform, etc. their data, and ensure that the standards that are defined are applied by all the teams that are managing their own data. And this is a new paradigm in the sense that the shift is very slow. There are some GAFA teams that are already in this paradigm, but most standard and more classical companies are still in the centralized paradigm and slowly shifting towards the data mesh paradigm. So do you have any questions on this part on the relationship between infrastructure and the ease of auditability of systems? Okay, so if there are no questions, I suggest we go to the conclusion of this course. So basically, until now, we saw that the three pillars of AI ethics are intelligibility, non-discrimination, and auditability. We saw that you can go to some very complex considerations on explainability, either from the technical level or from the sociological level. For example, who is my audience and how do I produce clear explanations for them, etc. But often when companies are get interested in AI ethics, they are a bit confused about how should we start dealing with this problem. Where do we need to start to produce more ethic AI systems? Even the fact that we present to them this idea of intelligibility, non-discrimination, and auditability, the problems to tackle seem so complex and of such large scale that they do not really know where to start to implement truly ethical assets. And what I want to present to you here is a framework that we developed to help think about how can I make concrete small steps towards more ethical AI assets. So basically, we start by helping them and asking them to define what are your ambitions, because you have a very wide array of ambitions on AI ethics. Some companies only want to communicate. They want to say that they are doing things on AI ethics to show that they are open-minded about the problem, or that they are taking action on a new field, etc. Some other companies might have very strong conviction on a specific aspect of AI ethics, for example, transparency, and they want to open source a lot of their code of AI systems. Some other companies, they want their targeting, their commercial targeting, to be done in a very ethical way. So these are very different types of ambitions, and we simply ask them to gather different types of participants in workshops and define what is the corporate ambition regarding AI ethics. So here I give a few examples. For example, you can ask that end customers should know when artificial intelligence was involved in the treatments concerning them, such as targeting through emails, etc. A second type of ambition can be, I want my client to be able to know what data was used to produce an AI recommendation or decision. For example, in the fifth type of ambition, I want to emphasize communication on the subject of the ethics of my artificial intelligence model. So here the focus is mainly on communication. And sixth is the one I mentioned about being able to access the code of the model that is being used to process the demand. So once you define your set of ambitions, then you need to clarify what are the answers to this ambition. So for example, for the first one, if you want your end customers to know that AI was involved, then you can add a message at the bottom of your page in communications with the client saying that, well, we use an artificial intelligence to target you with this email. You can even go further by adding, for example, the top 3 variables that influence the decision. For example, we saw that your revenue is below this, your age is in this tranche, and for example, you are of male or female sex. And this can give not a very strong reason, but at least an explanation and an intuition of why this person was targeted. For example, regarding the 6th criteria of accessing code, you can open source your code. For the 5th criteria, you can plan a communication sequence with end customers through, for example, specialized press. You can also try to build communication around tangible results that you achieved in ethical AI assets, etc. And now, once you have clarified the potential answers, you need to define what are the means to implement these potential answers. So for example, for the first one, you need to integrate to your tool of customer relationship management a new feature that will indicate whether AI or was used or not before sending the email, because of course sending of emails is completely automated. So you need to add a feature to this tool. In the fifth ambition, for example, you could exploit the results of implementation of ethical measures in data processing. For example, if you're already compliant with GDPR and you did something further than that, for example, you avoid using personal data or health data in pricing of your insurance, etc. You can communicate on this. In the sixth ambition, for example, on open sourcing the code, well, start by opening a company GitLab. And this step is often overlooked because to open a company GitLab, well, you need a lot of checks to be done by the compliance department, etc. And it might take time. So if you want to open source your code for example, in 3 months, you should start right now discussing this aspect of opening a GitLab. What are the processes to define the code that can go to the open GitLab or not, etc. And it's a process that can take months to define with the compliance departments, etc. And finally, once you have defined the means, you can estimate what is the cost for each of these ambitions and potential answers and ways and means to implement them. And once you have this information on cost, well, you can use this criterion and a criterion of, for example, what is at stake or the expected impact, etc., to classify all these ambitions, and then choose, for example, a top 3 or top 5 of ambitions that you will focus on, for example, for the next 6 months, and establish a roadmap of operational and concrete actions to turn AI ethics from a very conceptual and abstract field into a set of specific actions in a timeline and a well-defined roadmap. So to put a critical perspective on what we discussed, who defines the important questions to address? We gave some examples here of questions that most companies can think of. Basically, you will manage to have different stakeholders in workshops to discuss the problems and the ethical issues that they need to address, etc. But even if we think on the academic level, what are the topics of research in AI, etc., AI ethics, etc. If you remember, we defined in the beginning AI ethics as a fundamental questioning with no limits to questioning. And we often see that questions in AI ethics revolve about on explainability, non-discrimination, the end of the world for the public opinion. For example, with generally, if you ask them what is the problem with AI, well, it's AI replacing us or AI killing humans if they get too smart, etc. And of course, all these are very interesting problems in the sense that, of course, non-discrimination is an important problem. And of course, artificial intelligence systems replacing humans or leading to this killing of humans, etc., can be problematic. But often, what you can notice is a trend to focus on how problems. So, meaning, how can I make my artificial intelligence more explainable? How can I make my artificial intelligence system less discriminatory? How can I ensure that I am building systems that will be in good collaboration with humans instead of replacing them? But I think you should also focus more on the why. For example, why am I building this system? Why am I going to use artificial intelligence to build this system? Is it for pure performance? Is it for, did I analyze all the impacts of this automated increase of performance on all the stakeholders, either users or employees or society in general, etc.? What can be the unexpected uses that can be made of this system if it were to be developed? A good example of this is Amazon's recognition tool. So it's a computer vision tool that is used to recognize faces, and they evolved it to recognize faces even when they are masked. So basically, yeah, you can say that this is a cool feature, especially during this COVID period, so that you can use this tool even now that people are masked. But you can also ask yourself, is it really a good thing to develop such a system? Because of course we have this very hard and very weird period where of COVID, where we need to wear masks, but probably the use of this tool will extend far beyond this period and probably be used, for example, to analyze videos, security videos, etc., during protestations, etc. And of course, this can lead to a deviation of use from current situations to more securitarian situations, for example, for political control or sociological control. So is it really a good thing to add a feature like this to an AI system? And of course, you can ask yourself this type of question regarding the development of AI systems by themselves and not just adding features to them. And in this sense, if you remember, as I said, AI ethics is not a technical philosophy. It's not about the interpretation of how models should be understood, etc. It's really a techno-political philosophy in the sense that any choices you make, either in the questions that are being addressed or the models that are being built, or the way the models are being built regarding explainability, non-discrimination, or auditability, have political impacts and should be analyzed from this respect if we are to have a complete understanding of the tools we are concretely building.